Hi everyone, my name is Huanyu and I'm currently a PhD student in KTH Royal Institute of Technology in Stockholm, Sweden. Today I'm going to talk about multi-source training deep learning side-channel attack. I did this project with my colleagues, Sebastian Forsmark, Martin Brichfors, and my supervisor, Elena Dubrova. Okay, firstly, I want to explain what is this talk going about, what will you hear and see in the next 15 minutes. We know that half of century of research on multiple value logic shows that multiplicity can help solve many problems more efficiently. So our story is about using the multiplicity to implement a more efficient deep learning side-channel attack. And afterwards, we explore to which extent the negative impact caused by the board diversity can be mitigated by training deep learning models on multiple types of profiling boards. But let's start from the beginning. So I guess most of you may probably know what is side-channel attack. Even theoretically, secure cryptography may be broken since the encryption has to run in hardware and software at some point to actually do things, right? One big problem we have is that the physical implementation is not perfect. There might be some unintentional physical leakage during the execution of a cryptographic algorithm. For instance, during the encryption process, the power consumed by the victim device might be different according to the different input data. By analyzing the side channel signals in this example is the power consumption trace. The attacker is able to obtain some intermediate value of the encryption process and hence derive the secret key. This is called side channel attack. It is particularly threatening since once the secret key is leaked, the ciphertext can be decrypted and the signature can be forged. Recently, with advances in deep learning, side-channel attacks got a powerful ally. Deep learning techniques are good at finding correlations in raw data. With the help of deep learning techniques, it is much more easier for the attacker to find the correlation between the captured power traces and the secret key. This makes the side-channel attack more efficient. So how does a deep learning-based side-channel attack actually work? Generally, it is done in two stages. The first stage is called profiling. We assume that the attacker has a full control to a profiling device which is similar to the victim device. The attacker can capture a large set of power traces and record the corresponding information such as the input plaintext and keys from the profiling device. Afterwards, the selected type of deep learning model is trained to learn a leakage profile between traces and the key. Then, at the attack stage, the attacker can use this trained deep learning model to classify traces captured from the victim device and easily obtain the secret key. One of most widely used symmetric cryptographic algorithm is AES, Advanced Encryption Standard. We took AES 128 in our experiments, which has 10 encryption rounds in total. It is a block cipher, takes an 128 bits plaintext as the input, and the output is same length ciphertext. Also, the key length is set to 128 bits. The mode of operation in our experiment is set to the electronic codebook. Not really for scaring you, but I want to give you some ideas to what are the possible targets of AES up to now. For example, some works are achieved to use only one power trace to break an 8-bit microcontroller program to AES 128. Also, a tandem deep learning side-channel attack was proposed to break an Arctic 7 FPGA manufactured by using 28 nanometer process technology. What's more, one of my colleagues successfully recovered the secret key from a smart card within 10 traces recently. Wow. However, we know that the attacker doesn't have full control to the victim device, which means that the deep learning model should be trained on another device called profiling device. Now the problem is that the board diversity between the profiling device and the victim device may significantly reduce the attack accuracy. Even the trained model can achieve a 96% attack accuracy on the profiling device. When it comes to the victim device, the attack accuracy may drop to only 13%. So how to mitigate this effect and how to achieve a more efficient deep learning side channel attack? This becomes our research goal. To solve the problem and to achieve our goal, our hypothesis is that the multiplicity in the training data should be a good way to go. In other words, by training a deep learning neural network on traces captured from multiple devices instead of one, it may mitigate the effect caused by the board diversity. We believe that the multiplicity in the training dataset could help deep learning models to generalize better. So we designed our first experiment to verify our hypothesis. As you can see in the picture, we have one victim board which contains an 8-bit ATX Mega 128 D4 microcontroller, which is programmed to a standard AES 128. We call this type of board X-Mega. To capture traces, we use a tool called Chip Whisperer, and to build multiplicity in the profiling data, we capture traces from at most 9 other X-Mega boards to train deep learning models. All these profiling X-Mega boards are as the same as the victim board, and all these profiling boards and the victim board are programmed to the same version of the AES in our experiment. So here is an example of a captured power trace which contains all 16 S-box substitution of the first round of AES. It is captured during the execution of the encryption. Most of existing works use a divide and conquer strategy to recover the full key. It means the 128-bit key is firstly divided into 16 subkeys, and then these subkeys are recovered independently. In our project and in this presentation, we just focus on the first subkey and the others will be the same. The second picture shows a part of the captured trace, which contains information which is only related to the first subkey. Architecture of our deep learning model is shown in this table. We use a multiple layer perception network which with 4 dense layers. The identity model is used as our power model, which assumed the power consumption during the execution of the AES is proportional to the value at the attack point. The power model defines the number of outputs in a classifier. For example, if the data is a byte, the identity model leads to the set of 256 classes, which is the size of our output layer. Remember that our first experiment is designed to evaluate how the multiplicity in training dataset can affect the performance of deep learning side channel attacks. We train our models on at most 9 X-Mega boards and test these models on traces captured from the victim device. We found that with more sources for the training data, the model can achieve a higher attack accuracy. For example, as you can see in the result, when the model is trained on traces captured from only one XMega board, this model can recover the key from a single trace captured from the victim device with around 40% accuracy. However, when it comes to the model trained on traces captured from 9 XMega boards, the single trace recovery rate increased to 86%. So from this result, we can easily conclude that it is important to train deep learning model on traces captured from multiple devices which are as the same as the victim board. But there is another question. How about if we use some different types of board for profiling? So the second experiment is designed to evaluate to which extent the impact of board diversity can be reduced by training on more than one type of boards. In the previous experiment, all of the profiling boards are as the same as the victim board. I think you are still remember that. They all have the same printed circuit board. Now, we train models on traces captured from two different types of XMega board. We refer these two types as XMega 1 and XMega 2. The victim board and 3 of profiling boards, as you can see in blue in the picture, are belong to the XMega 1. Other 3 black boards in the picture are called XMega 2. Both XMega 1 and XMega 2 are programmed to the same version of AES. So we use at most 6 profiling boards in total in this experiment. We train models on these profiling devices and test these models on the victim board. We found that even if we train deep learning models on traces captured from 2 different types of board, we can still increase the key recovery rate. From the table, the result table, we found that when we use the model trained on 3xMega 1 and 3xMega 2, we still achieved a 55% attack accuracy. However, in our first experiment, we have showed that when the model trained on 6 devices, which are as the same as the victim device, the attack accuracy is around 80%. Which is better than using 2 different types of profiling boards. So by comparing these 2 experiments, we know that using multiple profiling boards, which are as the same as the victim board, should be a better way to go. So in conclusion, firstly, we show that it is important to train models on traces captured from multiple devices. Otherwise, the deep learning side channel attack accuracy may be not as good as the expectation. And secondly, we show that using the same type of board as the victim board for profiling is also important. Many interesting open problems remain. Certainly, the most important thing is how to design countermeasures against deep learning side channel attacks. We are definitely good guys, not the bad guys. This is the reason why we implement side channel attack. Because we want to know the side channel attack better, and hence we can do it more to design some good countermeasures in the future. So here are some references in the slide, and I've got times for questions. I will be happy to answer you. Thank you.